So welcome to Robotics 1. Once again, today's lesson is super important. So super important lesson. And in today's lesson, I'm going to work out homework 4. Also, I just want to let you know that there is a mismatch in the number of lessons on Canvas. I think I misnumbered lecture 19. But other than that, all the material, all the video lectures are available on Canvas. So if you need to review the material, you are welcome to go back to Canvas, click on the link, and you should be able to review the material. Now, I need to caution you, when I work out this problem, you are going to feel that this problem is actually super simple. So I'm going to set up the problem. One thing I just want to tell you that this is an extension of the homework 3. So let me set up the problem. In this problem, what we have is, this is the homework 4 problem. We have a revolute joint. Then there is another revolute joint. And then there is this link. And there is another link at the end. So this is a revolute joint. This is a revolute joint. This is a revolute joint. Now this revolute joint is R, 90R, because these two revolute joints are perpendicular each other, and that is parallel to R. So in homework 3, we just had R90R. So we did not have the last revolute joint, but in this problem, we have the last revolute joint. Now the L1 is the length of link 1, L2 is the length of link 2, L3 is the length of link 3. Now, if you want to draw the kinematic diagram for this robot, then the kinematic diagram for this robot can be drawn something like this. So you have a robot, something like this. Then there is a revolute joint. Then there is another revolute joint. And there is the end effector. So you have this end effector, you have this revolute joint, you have this revolute joint, you have this revolute joint. Now what I'm going to do is, I am pretty sure that you must be very comfortable by now in coming up with the coordinate systems. So if you want to set up the coordinate system, you will set up the coordinate system as Z0. Then say you will have this at Z1, then you will have this at Z2, and then you will have this at Z3. And then you can actually set up the coordinate system something like, you're gonna have X naught, you're gonna have Y naught, X naught, Y naught, then you have Y1, and then you're gonna have X1, and so on. So I'm not gonna spend time in setting the coordinate system, but what I want to tell you is, let me give you the rotation matrices for this problem. So if you look at, and my suggestion to you would be, as I'm working out the solution, please compare your answers. So 0R1 is going to be cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0. Then you have 0, 0, 1 multiplied by the projection matrix 1, 0, 0, 0, 0 minus 1, 0, 1, 0. And that gives you cosine theta 1, 0 minus sine theta 1, sine theta 1, 0 minus cosine theta 1, and then you are going to have 0, 1, 0. So this is the 0R1, 0H1 is something like cosine theta 1, 0, sine theta 1, sine theta 1, 0 minus cosine theta 1. So L1 cosine theta 1, L1 sine theta 1, 0, 1, 0, 0, 0, 0, 1, 0. Moving on, what I want to do is I will skip a step and give you 1H2. 1H2 is cosine theta 2 minus sine theta 2, 0, L2 cosine theta 2, sine theta 2, cosine theta 2, 0, L2 sine theta 2, 0, 0, 1, 0, 0, 0, 0, 1. And last but not least, which is 2H3 is cosine theta 3 minus sine theta 3, 0, L3 cosine theta 3, sine theta 3, cosine theta 3, 0, L3 sine theta 3, 0, 0, 1, 0, 0, 0, 0, 1. Now, I want to specify and make certain things very clear. What you have here, 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 and here, these are the distances between the frames. So what you want to, so finally, what you are going to do is you are going to have 0 H3 is equal to 0 H1, 1 H2, 2 H3. And you can solve this using MATLAB, and that gives you the forward kinematic equation. So this gives you the forward kinematics. However, at this point, I want to tell you a few things. Let's go back a minute. So what we have is we have a link here, but the mass of the link is at the center of the link. So mass of the link is at distance L1 by 2. Mass of the second link is at distance L2 by 2. And mass of the third link is at distance L3 by 2. So when we are trying to find out the potential energies or kinetic energies, we are interested in the distances. And let me show you what distances I'm interested in. I'm interested in this distance. I'm interested in this distance. And finally, I'm interested in this distance. So I'm not interested in the end effector. So if you right now, if you look at H03, H03 gives you the total transformation starting from the 0th frame to the end effector. But when we are trying to find out the kinematics, we are interested in finding out the positions or the velocities of mass m1. Here is, I'm going to call this m1, mass m2 or mass m3. I'm interested in the distances of m1, m2, and m3. So now, how would I make changes in this equations so that now the distances would be with respect to m1, m2, and m3. Now, please follow this carefully. Now, if I want the distance from m1, I'm gonna call this maybe something like, let me look at my sign convention, just a second. I'm gonna call this HM1, HM101. So something like this. And why is it HM1? Because I have cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0. And this is going to be L1 by 2 cosine theta 1, L1 by 2 sine theta 1, then I will have 0 and I will have 1. So this transformation is actually the distance. This transformation is for 0 to HM1. Now I need to find out for distance to the second mass, for distance to second mass. Now for that, I need to change my matrix 1 HM2 2, and this matrix is going to get changed cosine theta 2 minus sine theta 2, 0, L2 by 2 cosine theta 2, sine theta 2, cosine theta 2, 0, L2 by 2 sine theta 2, 0, 0, 1, 0, 0, 0, 0, 1. Now, once again, I need to be specific. So if you look at the way our system is, I am interested in finding out the distance M2, distance from M2. So right now, this HM02 is corresponding to the frame 1 to the mass M2. Now, same thing, I will have to do it for HM3 2 to 3. And that gives me something like cosine theta 3 minus sine theta 3, 0, L3 by 2 cosine theta 3, sine theta 3, cosine theta 3, 0, L3 by 2 sine theta 3, 0, 0, 1, 0, 0, 0, 0, 1. Now, if you look at what this transformation is, this transformation is actually something like up to this M3. So this transformation is from here to here. Now, finally, please note, I have with respect to 1, with respect to 2. So when I'm trying to find out the absolute distance, I need to do 0HM2, which is 0H1 multiplied by 1HM2, 2. And when I'm interested in 0HM3, which is the transformation from the base frame, 0th frame, all the way to M3, then I need to do 0H1, 1H2, and 2HM3, 3. Everyone understood? That is the difference between the previous case, wherein H01 is the distance between the 0th frame to first frame. But I really need from 0th frame to mass M1. And then I would use all this information to find out the distances from the second and third mass. Trust me, once I work out the problem, you will see that this problem is very straightforward. The only thing is you have to systematically follow it through. Now, next step is we have to find out positions of mass M1. So how do we find out positions of mass M1? Position of M1. Position of M1 is you have 0HM1. 0HM1, the last column is gonna give you the positions of mass M1. And you have that information already. So this is the position of mass M1, position of mass M1. So I'm gonna call this M1 underscore PX, M1 underscore PY, and M1 underscore PZ. Now the next step is you have to do something similar, 0HM2. And when you find out the 0HM2, you are gonna have 1, 2, 3, and 4. This is going to be M2 underscore PX, M2 underscore PY, and M2 underscore PZ. A word of caution though, 0HM2, you need to have complete 0H1, not 0HM1. You need to have 0H1 multiplied by 1HM2, 2. And that gives you same thing you will have to repeat for 0HM3, wherein you will have 0H1, 1H2. Please note, these two are complete matrices. No half lengths appear in these matrices. And then you will have 2HM3, 3. And then once you have this matrix, the last column is going to be M3 underscore PX, M3 underscore PY, M3 underscore PZ, and clearly you are going to have 1 over here. Everyone understood this? Now the next step is, how do we find out the Jacobians? And finding Jacobian is actually very simple using MATLAB, and I will show you. But what I want you to understand is you already have the rotation matrices contained in your homogeneous transformation matrix. This is 0, R1. This is 1, R2. And this is 2, R3. So you can grab these components of the matrices and you already have the rotation matrices. And now I'm gonna go through my MATLAB script, and actually I will kind of write line by line the MATLAB script. This would be the perfect time to open MATLAB and follow with me what I'm doing. And I just want to tell you that I'm gonna make use of some shortcuts that will make life easy. So basically I will try to get Jacobian directly from the MATLAB, angular velocity Jacobian directly from MATLAB. I did not use these shortcuts in my earlier lesson because I didn't want you to get confused. But since now we know the flow, I will actually switch my screen. I will share my MATLAB screen, and then we can work out the problem. So bear with me. I'm gonna now switch to MATLAB. But before I proceed, any questions? Okay, now you should be able to see my MATLAB screen. So, and again, I'm gonna go very slowly. And if you have any questions, please ask me in the chat window. I would be looking at my chat window. So the first step in MATLAB is I always start with something like forward kinematics, and then I'm gonna paste. So this is just to clear the MATLAB screen and windows, just so that to make sure that there are no residual variables. In this problem, there is theta 1, theta 2, theta 3. Then I have theta 1 dot, theta 2 dot, and theta 3 dot. So in line number 4, I'm going to define my symbolic variables. T1 stands for theta 1, T2 stands for theta 2, T3 stands for theta 3, TD1 is theta 1 dot, TD2 is theta 2 dot, and TD3 is theta 3 dot. Any questions here? Next line, I'm gonna just define my lengths and masses. So, and these come from the problem. So G is the gravitational acceleration. G is the gravitational acceleration. M1 is the first mass in kilograms. M2 is the second mass in kilograms. M3 is the third mass in kilograms. Length L1 is 0.5. Length L2 is 0.5. Length L3 is 0.25. Any questions here? Next thing is I'm going to find out moment of inertias around the centroid of axis. So I1 is the moment of inertia of the first mass around its center. I2 is the moment of inertia of the second mass around its center, and I3 is the moment of inertia of the third mass around its center. Now, at this point, I need to sort of tell you what exactly is happening here. Now, and for that, I'm gonna go switch back to my whiteboard, the computer screen. So okay. Now, if you look at this problem, we want to be comfortable with what are the IXX, IYYs, and IZZs. Now, just check this out. So, and this needs a little discussion. So you have the first revolute joint, and this first revolute joint has this link. And I'm going to show you slightly enlarged version. This we are considering as a slender rod. And when we are considering this as a slender rod, this length is L1 and the mass is M1. Now let me just tell you the X, Y, and Z rotations of this. So this is my Z. Now I have, this is my Z naught. Then I have assumed this to be my X naught, and I have assumed this as my Y naught. Now, if you look at IXX1 is nothing but I1. IYY1, so IYY1 is nothing but I1. Now the question is, what is going to be IZZ1? So the question is for IZZ1, now if you look at the way we have worked out the problems in the past, we IXX, IYY for slender rod, IZZ, actually IXX, sorry, IXX is 0. IXX is 0. IXX is 0. IYY is I1. IZZ is I1. And the reason for that is, I just want to tell you, is you need to assume the coordinate system something like this. So IXX is 0, IYY is 1, IZZ is 1, I1. So what is value of I1, which is M1 L1 square by 12, M1 L1 square by 12. And IXX, yeah, IXX1 is 0. Yeah, IXX1 is 0. Now, so you have all this information. And where is this information going to get used? And this is something important. When we are going to find out the kinetic energy, IXX1 is gonna get multiplied with omega x square, omega x1 square. IYY1 is gonna get multiplied by omega y1 square, and IZZ1 is gonna get multiplied by IZZ1 square. So you just want to be careful with that. Now what I'm going to do is I'm going to add the second link, but just for the sake of simplicity, I'm going to show the second link attached to this link. So this is my second link. So again, I am going to consider my mass M2 over here. And for mass M2 here, I need to do the exact same thing. I need to place my X, Y, and Z, which are exactly similar to X0, Y0, and Z0. And again, when I do I XX for mass 2 is going to be 0, I YY for mass 1, mass 2 is going to be I2, and IZZ for mass 2 is going to be I2, and I2 is going to be M2 L2 square by 12. Everyone understood this? The last part is I have the last link, which is over here. And now you know the logic. Same thing, I'm going to have X0, Z0, and Y0. And then I'm going to have I, Z, IXX3, IXX3 is equal to 0, IYY3 is equal to I3, and ICZ3 is equal to I3. And I just want to write this down separately because we are going to need this information. So I'm going to repeat what I said. For link 1, I1 is equal to M1 L1 square by 12. I XX1 is equal to 0. I YY1 is equal to I1. I ZZ1 is equal to I1. For link 2, I2 is equal to M2 L2 square by 12. Same thing, IXX2 is equal to 0. IYY2 is equal to I2. IZZ2 is equal to I2. For link 3, I3 is equal to M3 L3 square by 12. I XX3 is equal to 0. I YY3 is equal to I3. I ZZ3 is equal to I3. And this information will be needed when we try to find out the angular velocities. Because please note, Ixx will get multiplied with omega x1 square. Iyy will get multiplied with omega y1 square. Izz will get multiplied with omega z1 square. Again, omega x1 square, x2 square, omega y2 square, omega z2 square. Last but not least, omega x3 square omega y3 square omega z3 square. So this information will be needed when we work out the problem. Any questions at this point? Now I'm going to go back to MATLAB. So now we are on MATLAB. So I'm just going to say, let me just say here, just for our reference, I xx, I yy1, I zz1, I yy2, I zz2, and here, last but not least, I yy3, I zz3. Now, what I'm going to do is, I'm going to duplicate, I'm just going to write h01, h12, h23. So the next step is homogeneous transformations. And we have derived these. And what I will do is I will input these in the chat window. So h01, h12, and h23. Now we want to solve, first and foremost, the forward kinematics problem. So for that, what I'm going to do is I'm going to find out h02, and then I'm going to find out h03. So h02 and h03. And at this point, what I'm going to do is I am going to run this code. So please run this code and then type h03. Oh, h03. Now, can you see my h03? Does it match with whatever you have? So now let's find out what we have. You have cosine T2, T3, cosine T1, cosine T2, cosine T3, sine T1. Then you have sine T2, T3, cosine T1, sine T2, T3, sine T1. Solving the inverse kinematics problem for this particular homogeneous transformation is fairly simple. And the reason for that is, look at the rotational matrix. So if I were to say h03, 1, 2, 3, comma, 1, 2, 3. So this is 1, 2, 3, comma, 1, 2, comma, 1, 2, 3, comma, 1, 2, 3. So if you look at this, This is actually your 0R3. You will notice that the last column has sine T1 and cosine T1. So you will know the orientation of the end effector. So this value will be given to you. Since you know this value, you can actually find out the tan equation or sine equation and find out what is the value of theta 1. So to solve inverse kinematics, you will find out, and I will just give you the hint here in the code. Use 0h3 to find T1 first. So from this element or this element, you can find out the value of T1. Now, the next thing is, I want you to look at the last column of H03. H03, all rows, fourth column. So if you look at H03, all rows, fourth column, this is nothing but X location of the end effector, Y location of the end effector, and the Z location of the end effector. This will also be known to you. And what you can do is, you can actually look at the solution. So think about it like you got cosine theta 1 known. You can find out sine theta 1 that is known. And the only two unknowns now you are left with is, if you think about it, you got cosine theta 2 cos and theta 3, theta 2, theta 3, and then you have cosine of theta 2 and theta 2. But check this out. This element is same as this element. You already know cosine theta 1. So in this first row, first column, you know this value. You can actually find out what is the value of cosine T2 plus T3 is and substitute that in this expression. Once again, this value is known to you. You find out value of theta 1, substitute the value of theta 1, and then get the value of cosine theta 2 plus theta 3. Substitute the value of cosine theta 2 plus theta 3 in this expression, and the only unknown that is left is cosine T2. So here I actually give you the hint. First use H03 to find T1 first. So you can find out T1 from this element. Then you can use first row, fourth column, which is this guy, to find out T2. And finally, then you can find out T1. Everyone understood how to solve the inverse kinematics problem? And to be honest with you, this is one way to solve the inverse kinematics problem. There are different ways to solve the inverse kinematics problem, but this is one way to solve inverse kinematics problem. Any questions here before I proceed further? I'm looking at the chat window. Now, next thing is the positions of masses. And this is exactly what did you substitute. I did not substitute anything. What I'm just saying that to find the inverse kinematics, you can find out the value of theta 1 from this equation, then substitute the value of theta 1 in this equation. That gives you cosine theta 2 plus theta 3. Once you find out cosine theta 2 plus theta 3, that can be substituted in this expression and you can find out the value of theta 2. Once you know the value of theta 2, you already know theta 1, you can find out the value of theta 3. Trenton, did you understand? Okay, fantastic. Now we are gonna do the same thing for the positions of masses. So for positions of masses, I'm gonna start with the first mass. Now check this out. The HM101. So the way you can read this is HM1. So this is for mass M101. Rotation matrix remains the same, but this mass M1 is at half of the distance. That's why this is L1 by 2. This mass is at half of the distance, thus L1 by 2. So matrix for mass M1. Now you will do the same thing for mass M2. This is for mass M2. And you want actually to find out the location of mass M2 with respect to the 0th frame. And when you want to do that, you need to multiply that with H01 and HM2 212. So you will have these. Same thing we have to do for mass M3. And you will have to find out the location of mass M3 with respect to the 0th frame. So the key parameters or key components here are HM202, because this gives you the homogeneous transformation matrix for mass M2 with respect to the 0th frame in the inertial frame. Other important part is HM101. This gives you the homogeneous transformation of mass M1 with respect to 0th reference frame. And last but not least, HM30T gives you the homogeneous transformation matrix of mass M3 with respect to the 0th reference frame. The way I can decipher this is M3, which means the homogeneous transformation matrix is for mass M3, that is relating 0th reference frame to the 3rd reference frame. So this is how this code can be written. Next obvious step is we need the positions of the mass M1, M2, and M3. This is actually very simple. So I'm gonna show you the trick here. So HM101, the 4th row first column is the position, X position of mass M1. The second row 4th column is the Y position of mass M1. And the 3rd row 4th column is the Z position of mass M1. So M1PX is the X position of mass M1. m1 underscore py is the y position of mass m1. m1 pz is the z position of mass m1. Everyone understood? Now, next thing, I'm gonna do the same thing for mass m2, but in the case of m2, instead of hm101, it would be hm202, hm202 second row fourth column, hm202 third row fourth column. So these are the positions of masses. Now we have to do the same thing for mass m3. And you will do the same thing for mass m3. Everyone okay so far? Any questions at this point? I'm looking at the chat window, so if you have any questions, ask me now. Now I'm gonna show you a simple trick to find velocity. And I discussed this in the lesson that there are two ways to find velocities. I can actually get this m1px and find the derivative. I can do m1py, find the derivative, m1pz, find the derivative, or as a shortcut, I can just take the Jacobian. And this is how I'm doing this. So it's just a shortcut method. So to find velocities, what you do is you take the Jacobian of m1px, m1py, m1pz with respect to theta 1, theta 2, and theta 3. This gives you the Jacobian. So the velocities, that's overall velocities, m1 overall velocities are nothing but the Jacobian multiplied by the angular velocities. And boom, now you have the velocities of mass m1. So same thing you can do for velocities of mass m2, but now you need to find out the Jacobian of m2px, m2py, m2pz with respect to theta 1, theta 2, theta 3, and the velocities of mass m2 are these Jacobian JL2. This is the Jacobian we found, multiplied by again the angular velocities of T1, T2, T3. So this will be TD1, TD2, and TD3. So now we will do the same thing for mass 3. And this is going to be for mass 3. Now at this point, I'm going to take a super shortcut. So I want to find out the total linear kinetic energy. Total linear kinetic energy is nothing but this velocity m1 squared. Individual terms of this m1 underscore v needs to be squared, multiplied by mass m1 and multiplied by 0.5. The individual velocities, okay, let's run this code for a second so that it will be clear. Let me run this code. And I just want to show you what I get here. M1 m1 underscore v. So m1 underscore v, this is the velocity in the x direction for mass m1. This is velocity in the y direction for mass m1. And this is the velocity in z direction for mass m1. If you were to do the same thing for m2 underscore v, this is the velocity of mass m2 in the x direction, velocity of mass m2 in y direction, and velocity of mass m2 in z direction. And we already substituted the value of m1, m2, so it's all taken care of. To find the total velocity, what I'm going to do is I'm going to give you a very simple equation and I will explain it to you how this works out. So this equation is something like this. So what I'm trying to do here is, check this out. m1 underscore v is the velocity vector. I'm doing a dot square, which means each element, this element will get squared, this element will get squared, and this element will get squared. m2 underscore v dot square, which means the first element will get squared, the second element will get squared, and the third element will get squared. And what I want is I want sum of all those squares. So I have this sum. So when I sum, I get the square of velocities added. Then what I do is I multiply those sum of square of velocities by mass m1, sum of square of velocities by mass m2, sum of square of velocities for mass m3, and multiply those by individual masses. So now m1, so what this equation means is m1 v1x square plus m1 v1y square plus m1 multiplied by v1 z square. This expression is m2 multiplied by summation of the squares of individual components of velocity. So boom, this is your linear kinetic energy. And that is what we will use when we try to find the Lagrangian. Any questions at this point? The next thing is, just for the completion's sake, I want would be the same as extracting values from the velocity matrix. Yeah, they should be the same values. You can extract those and then use those. Your answers would be the same. Next thing is, if you want to find out the Jacobian, which is the linear Jacobian, comes from H03. That is, again, you can use the matrix Jacobian function. But note, you need to first have the square bracket H03142434 with respect to T1, T2, and T3. And at this point, you are welcome to run this code and get the values of M1, M2V, M3V, and so on. So let me see, how far did we run earlier? Velocities for M3, M3, okay. So I can run this code and then see that code ran. So at this point, if you were to just say T underscore L, that is the expression for the linear kinetic energy for mass M1, M2, and M3. Are you with me so far? Now comes the tricky part, and we should actually go a little bit slower. So let me let's see. T total velocity of mass m3. Let me add this. I missed this line of code. Now the next is angular velocity of I1. And angular velocity of I1 will come from the R01, which is nothing but the first 3x3 matrix of your H01. That gives you the angular velocity of I1. Now let's do this, and then you will see what happens. So angular velocity of I1 is TD1 multiplied by sine T1, TD1 multiplied by cosine T1, and then the last but not least is going to be 0. So first link will have angular velocity in x direction. It will have angular velocity in y direction, and it will have the angular velocity in z direction. So that is going to be for the first one. Now there is something else I need to clarify. Actually, let me w underscore I1 is equal to, basically it's gonna be 0. So identity matrix multiplied by 0, 1, TD1. So this will be for I1. This will be for I2. So because if you look at 0 R0, that is an identity matrix. Identity matrix gets multiplied with 0, 0, TD1. So this gives you WI1. So 0, 0, TD1. For WI2, what you will do is you will have W underscore I1 plus H01. This is going to be R01 multiplied by TD2. And when you do this, you are going to have WI. So let me type it over here. This is going to be W underscore I2. And W underscore I2 is going to give you TD2 sine T1, TD2 sine T2, and TD1 as its omega z. So I just need to write this here. WI2 is equal to W underscore I1 plus H01 and TD2. So this is the angular velocity of I2. Now the next part, the last part, is angular velocity of I3. To find angular velocity of I3, you will be doing the same mathematical jugglery on the last. So you are going to have, and I will modify this in just a second. This is going to be W underscore I1 plus W underscore I2 plus H02 1 to 3 1 to 3. So this is going to be R02 multiplied with TD. So I'm going to do angular velocity okay. Yeah. Actually, you're right. You're right. Yeah. Sorry. We will just correct. We will just add W2. Correct. WI2, not WI1. So this is the equation. Okay. Now I'm going to run this. And you will, what I want to do is, I want to find, just do WI underscore WI W underscore I3, W underscore I3. Now W3, yeah, W3, so angular velocity, and actually that's a good question. Let me answer that question, and I will, Borna, it's a good question. Just a second. Now, before I proceed further, I want you to understand this expression. So WI1 is the angular velocity of the first link. WI2 is the angular velocity of the second link. WI3 is the angular velocity of the third link. Now, please note, there is no link before the first link. There is no link before the first link. That's why whatever WI1, yeah, just a second. I will answer that question too. So basically, WI1, there is no link before the first link. So you have an identity matrix multiplied by 0, 0 TD1. So now if you look at W underscore I1, W underscore I1, notice there is no velocity in X direction. There is no velocity in Y direction, but there is a velocity in Z direction. Now I want you to look at W12. W12 is already, it consists of the angular velocity of the previous link, but and addition to that, the angular velocity of the first link. Now it is super important that I want you to note that this is H01, because this entire angular velocity needs to be with respect to the 0th reference frame. So I will say that once again. This is H01 because we want the angular velocity with respect to the 0th reference frame. That's why we have the transformation matrix H01 and not H12. Does that answer your question, Trenton? H01 tells me, this gives me the mapping from the angular velocity vector, angular velocity of link 2 with respect to the angular velocity with respect to the ground reference frame. Because check this out, Wi1, omega I1 is with respect to the 0th reference frame. So omega I2 must be with respect to the 0th reference frame. Omega I3 must be with respect to the 0th reference frame. So hopefully that question, the Trenton's question, is answered. Now let me answer Borna's question. Now think about it like this. Link number 2 is not attached to ground. Link number 2 is attached to link number 1, which means the angular velocity of link number 1 will get added to the angular velocity of link number 2. Link number 3 is not attached to frame 0, but it is attached to frame 2. So which means the angular velocity of link 1, angular velocity of link 2, and angular velocity of link 3, all they need to be combined. But as rightly pointed out by Jade, angular velocity of link 2 already consists of angular velocity of link 1. So I just add angular velocity of link 2. Okay, now just a second here. Let me finish this discussion here. Now, the last but not least is to find angular velocity Jacobian. What you need to do is, I'm going to give you a small trick. So if you look at, yeah, it has to be R02, not R12. That, so Bao, I will answer your question, but let me finish this in just a second, because prepare to be amazed. So now we have Wi3, and I'm going to write this down, W omega I3. Now what I want to do is, I want to extract the Jacobian matrix from this expression. I want to extract the Jacobian matrix from that expression. And MATLAB has a command for that. And the command for that is equations to matrix. So I'm going to use, I did not use this command earlier, but now I'm going to introduce this command. This command is called equations to matrix. And when you use this command, equations to matrix, MATLAB will directly give you the solution. So the command is, I'm going to paste this in my MATLAB, and then I'm going to use that command over here and just say JWW, and now this is your Jacobian. So now if you do JWW, I'll show you uh, W underscore I3. So you have W underscore I3, which comprises of TD1, TD2, and TD3. TD1, TD2, and TD3. And you want to formulate, you want to get the Jacobian matrix. The command is JWW is equal to equations to matrix. And then you have to supply the equations. And in the square bracket, you need to supply the variables. And that will get you the Jacobian directly. Okay, it's 5:46. So I'm gonna stop here, but I will continue this problem in next class. But if you have any questions, I would be happy to answer. I'm gonna stop recording.